All right, so our second speaker this morning is Kevin Tyle. Kevin Tyle comes to us from the University at Albany, where he is the Senior Programmer and Network and System Administrator in the Department of Atmospheric Environmental Sciences. He is also the current chair of the Unidata Users Committee and an all-around stand-up guy, and of course, another Kevin, so there's nothing ever wrong with that. Today he's going to talk to us about how we can use Python to tackle big data in small scripts. Let's welcome Kevin.
Thanks, Kevin. We'll call this particular hour the K squared. So Kevin G, off to Kevin T. Just before I get started with the PowerPoint presentation, I do want to call your attention to the GitHub site, because there is some information regarding my particular talk. So what I think I might do is just give a couple of minutes to get folks prepared if they're not already. So once again, if you've installed the mini Conda, again, that's at the very top of the GitHub site. Hopefully everyone who wishes to participate in the hands-on will have done this already. So assuming that you have, all that you should really need to do for this, for my particular hands-on, is first of all, if you haven't installed the environments, you're going to want to do this third line from the top, the Conda create environment for my workshop session. And then what you're going to need to do to prepare yourself to actually get into the Python environment that I'll be using for my 4 hands-on examples is you're just going to want to type source activate workshop-Kevin. Now, for those of you who are on a Windows machine, my sympathies, but you do want to just eliminate source from that. So you're going to want to open up a command line window, and then you're going to type activate workshop-Kevin. So I think what I'll do is just pause for a couple minutes. I'll load up my PowerPoint, make sure people are ready for that. And if we scroll down just a little bit on the GitHub site, what I do have is a link to a zip file. Right now it's not on the Ramada server, but it's on my web server at Department of at UAlbany. If you click on the link, all you're going to want to do is download to extract a zip file. What I'd recommend that you do is that you download and then extract it in its own directory, because then what we're going to end up doing is we're going to start an interactive Python session, and it'll just go a little bit quicker if you're already CD'd into that directory prior to the launching of the hands-on. I'll give that just about a couple of minutes. In the meantime, I'll load up the PowerPoint, and then we'll get going with the talky portion of my session.
Repeat that URL there?
Where the
Sure, I'll put that back up, but once again, all you need to do is go to the workshop GitHub site, and the URL will already be there for you, and I'll be more than happy to put that back up. Okay?
All right, I just had to reload the GitHub.
Okay.
I've done all that, but I don't see the URL.
Oh, here we go.
Oh, there it is.
This is import water right now, so in Pythonese.
I think did it just get added? That just got added. Okay. I brought that up. Not now.
Okay, I think I'm going to get started with the formal part of the talk. And really what I'll be talking about today is just using Python now to connect to data sets big and small. And one of the themes of this year's workshop is big data, and I think there's various font sizes, if you will, of big, and so what I'm saying is big is probably really tiny compared to some of the huge data sets that are out there. If you consider, for example, any of the CMIP5 data sets that are out there. So we'll treat the term big data with a great degree of room in order to say what exactly do we mean by big. So there's the Wikipedia definition of big data that we talk about here, and I'm going to gear this first part of the talk to how we, in my particular department, and it's probably somewhat similar at many of the ATM, geophysical, oceanic science departments across the country. We have several members here. We'll go through that. But what do we mean by data? Well, here's some big data right here. Data doesn't necessarily have to be in bits. Well, here's about 2 feet of data, and of course the obligatory cat picture here. But with the data, in this case we have, one of the challenges is shoveling, but in terms of our virtual data, we have several different challenges, some of which include capturing and transferring and storage, visualization, and sharing. I'm going to talk particularly about these few aspects of the big data challenge today. Now, similar to many of the atmospheric science programs across the country, we've made great use of Unidata's local data manager software and the internet data distribution. And like many things, we were just talking with Mohan and Carlos Malzahn just a minute ago, and how software continues to get bigger. We had started with Google Chrome that was fairly small when it first came out, and now it's gotten pretty big. Well, the same thing comes with data that we've been ingesting. And of course, what we're seeing is that as, for example, model resolution gets greater and greater, both in terms of spatial and temporal resolution, the incoming data stream gets bigger and bigger. So currently at UAlbany, we're taking in a few hundred gigabytes per day, and we're storing it. This number is only going to go up. We have high-resolution data sets such as the HER, the GFS later this summer is going to start to become available over Unidata's conduit data stream at quarter-degree resolution. So it really becomes a problem, how best can we store data, and particularly what data do we really need to have sitting locally on, say, our department's network. I think the time has clearly come to start utilizing some of the technologies that have actually, as we'll see, been around for a couple of decades, being able to access very high-resolution data sets that aren't sitting on our network-attached storage in say, a department. And we'll also find that using Python is a very quick and easy tool where you can query some very large data sets that aren't sitting on your computer or your department's network, and actually be able to display stuff quickly and easily. So we'll go through these fairly quickly, but when we talk about storage in my department, well, we have network-attached storage and we have local disks. Obviously, there's a limit in terms of network storage as due to the increased expense, how many terabytes we can accommodate in our department. Now, there's different flavors of data. We can think of it almost in terms of colors, where we go from bright data that's very easily accessible. Anyone, say, in my department can access, say, today's GFS run very quickly. And then we start getting into progressively less accessible, or we'll call darker data. I could have, say, a wharf run that's just sitting on my local laptop here. It's available to me. It's it's quite a bit more difficult for someone else in my department, and certainly external to my department, to access that data. And we go down into even progressively less easily accessible data, and we can even talk about very dark data where the data actually is gone. So you have your your memory stick, and it goes in the washing machine, and well, that data is essentially gone and lost to you. So we really need to think about, in terms of our important data, we want to make it active and easily accessible, and not necessarily accessible inside one particular unit or department. Now, we'll do have a brief little talk about data types. The bulk of this talk is going to focus on gridded data from NWP models. But we've got all sorts of different flavors of data. Some of it's human readable text data. We've got satellite imagery, radar imagery, and we've got gridded data. Typically, we work with gridded data. When we think of gridded data, we're thinking of model output. But here's an example of human readable text data, which we're really not going to talk much about today. We have different types of image data, satellite and radar. And let's shift our focus now to gridded data. So here we have typically data that's generated through numerical weather prediction models, reanalyses such as the CFSR, and we can also typically take image data like satellite and radar and grid it as well. There's a GridSat data set that I believe NCDC hosts that has satellite data that's been written to a grid. Now in our department, and I think this is fairly extendable to other departments across the country, if not the world, when we're talking about viewing model data in a meteorological, that's meteorologically based, we have pretty much 4 types of ways that the data is written to file. There's GRIB, there's NetCDF, there's just binary format, which is bad, and then there's GEMPEG format. Now GRIB is a WMO standard. Pretty much any model data that's being generated, say, from NSEP, ultimately is placed on data servers that might be FTP, might be HTTP, and maybe OPeNDAP as well. But the format is GRIB2. Earlier versions were GRIB1, GRIB2 enables compression to make some of these very high resolution data sets a bit more manageable in terms of being able to store them on disks. Bad thing about GRIB is that we always have to worry about tables. One particular, a 500 millibar geopotential height ultimately is encoded into the GRIB file, and what happens is that a program then has to access a table to determine what a particular GRIB message actually stands for. In this case, a few sequences of tables and subtables actually point us to, say, a 500 millibar geopotential height field. Bad thing about decoding tables is that they can change, so it's theoretically possible that I could read in a GRIB file today, and then 20 years down the road, hopefully GRIB2 won't still be the standard, but it could be that suddenly that 500 millibar height field has been changed into updraft helicity. I mean, I'm not sure why that would happen, but it could happen, and it requires table maintenance. GEMPAC has a long and storied history. Many atmospheric science departments, especially including UAlbany, has used GEMPAC for many years, but it's its own format, It really is designed for visualization in GEMPAC and GEMPAC's NAWIP's graphical user interface to the GEMPAC libraries. Good thing is that the GEMPAC data format standard is really fairly static and has not changed over many years, and that makes for translation packages into, say, NetCDF fairly easy. Going the other way from, say, NetCDF into GEMPAC is more difficult, and as we'll see in some of the examples, that's because there can be many different flavors of a NetCDF file. And then we have perhaps someone who's generated data on a grid but doesn't feel like following a GRIB standard or a NetCDF or a GEMPAC standard. This becomes really difficult because at this point you really need to have your own program that's able, along with documentation of how this binary grid file may be written in order to read it. So we really want to move away from this type of not terribly well-defined standard for writing gridded data. So NetCDF is kind of the way to go. The big advantage of NetCDF is that it is a self-describing format. You can actually, once you read in a NetCDF file, in its metadata, it actually tells you everything about what's in the file, assuming that the person or entity or program that wrote those NetCDF files took the time to write in the metadata. And what Unidata has developed and enforces for many years is the climate and forecast data conventions. And the idea is that any type of NetCDF file that's been created using these conventions can then be easily read. It's sort of almost the lingua franca of reading in gridded data. It all follows the same type of format and can therefore be read by a multitude of programs. For example, as we'll go through and show some examples of programs that can read in gridded data that uses the NetCDF climate and forecast conventions. We won't much talk about point data. That really is a big issue, though, in the developing Python atmospheric science infrastructure. As great as gridded data is, I'm sure there are a lot of folks here in the audience who, really the important thing. Let's look at what's really happening. Let's look at the point data. Let's look at the observations, this is where I think there's an opportunity for some further growth in the Python world in terms of being able to visualize these very important types of data that don't fit nicely on a grid. So historically, in our department, when we wanted to transfer data or make it available externally, we put it on an FTP server or we put it on a web server. Or, if necessary, we copy it to a USB disk and take it across the hall or mail it across the world. But what we increasingly want to make ourselves, avail ourselves of is being able to access data sets that sit on an internet-connected server but use a type of data access protocol that's actually been around for a number of years, and it's called OPeNDAP, Open Data Access Protocol. And one of the great advantages is if you imagine that you go to an FTP site, let's say you've gone to NSEP's Nomads server, and you see that there is the latest run of the high-resolution rapid refresh model, and it's 2.5 gigs. Well, if you request that data via HTTP or FTP, it's going to take a while to download that file, and you're getting the whole kit and caboodle. Wouldn't it be nice if I just wanted to look at the radar, the forecast radar over, say, Boulder for the next 15 hours? Wouldn't it be great if I could just pull that out of only the information I actually need from a remote server? And that's what OPeNDAP allows you to do. So there are different types of ways that we can access data using OPeNDAP, depending on the type of server that we're using. There's Unidata's thread server, and there's Unidata's Ramada server. There's also one that we don't use in our department, the GRADS data server. GRADS is another very popular visualization program for meteorological data. And we'll also talk about using, say, IPython and IPython Notebook for visualization and accessing data from a OPeNDAP server very, very shortly. Now, Threads is Unidata developed, and built into it, it uses a translation library that's also developed by Unidata, the netcdf Java package. The cool thing about this is that we can take, say, for example, data from NSEP that's in GRIB2 format, and it is served through a thread server, and by the magic of netcdf Java, it will come to us as netcdf, and not just netcdf, but netcdf with the CF, climate and forecast data conventions. All this translation happens kind of magically behind the scenes. This is netcdf Java working for you. It will do the same thing for a GEMPEG file that happens to be hosted on a thread server. Threads also enables some other cool ways of visualizing things, such as WMS web map service. Ramada, originally developed at Unidata, and now continuing to be developed independently by the two developers, Jeff McWhirter and Don Murray, and available on SourceForge. Also leverages the netcdf Java library. It doesn't have WMS, but it allows publishing of data using some client tools such as Unidata's integrated data viewer, and it also obeys the netcdf Java library and therefore avails ourselves of the CF conventions. Now, GRADS, this is still used in a multitude of places, including NSEP nomads, and it also will translate GRIB2 data into netcdf, but it does it its own way. And this, as we'll see in a couple of the demos, will cause some problems. And it means that we can't just write one type of Python program that reads in netcdf Java and generalize it so it can read and work the same way depending on whether we're reading from a thread server or versus a GRAD server. And I have combed Google Images again and again, and GRADS, they don't believe in branding. I cannot find a GRADS image. So this is really the best I can come up with for an image. So that's where we go for GRADS. We'll talk briefly about some of the ways that we visualize data. There are several tried and true programs, and we're going to kind of wrap up with the new way, which is Python. But very popular is NCL. NCL is great because it's scripting. It has a wide variety of ways that you can tweak figures to produce publication quality graphics. And a very nice thing is that NCL for many years has supported OPeNDAP access. And one of the things that we'll talk about is that really what we're talking about in terms of accessing data using OPeNDAP versus these traditional ways, this really isn't new. NCL, for example, you can download and you are presented with the option, do I want DAP capability, data access protocol, or not? This capability has been available for many years, and it makes NCL really, really good at leveraging the ability to access very large data sets that we don't have to worry about hosting on our own network. IDV also does the same thing. Can access very easily OPeNDAP just by browsing catalogs. Okay, so Python very nicely can access data sets that are served via OPeNDAP via its libraries. what Python brings to the table are a huge amount of external libraries. And the one that we're going to leverage in our hands-on session, just a couple minutes, is the netcdf4 library. Once we import that library, that was developed by Jeff Whitaker right here in Boulder, and also with support from Unidata folks now. Using the netcdf4 library, we can query OPeNDAP servers and local data sitting on your own disk. And with just a few lines of code, we can put together some pretty cool maps. And there are plenty of other programs that speak OPeNDAP. Again, this capability, reading from OPeNDAP servers, isn't new. Then we have some programs that don't speak OPeNDAP. Genpack is still, in my opinion, probably the most comprehensive package of diagnostic programs, diagnostic libraries to query gridded data sets. But the problem is, it's an old program. It does not have any type of OPeNDAP capability. And the only way you can really leverage Genpack's formidable package of diagnostic tools is to download the grid file, which, as we said, could be several gigabytes. And then, not only that, convert it into specific Genpack format, because Genpack can only read Genpack formatted files. So a big challenge moving forward is to try to have, if we're thinking of Python as being sort of the new way, we've got to give the researchers and the educators the tools that they've come to rely on using traditional ways of visualizing and analyzing data. Okay, so what I'd like to do now is jump to the hands-on session. So assuming that folks have created the Miniconda environment and activated it, what we're going to do is actually run some Python, and we're going to generate some maps, we're going to generate some time series, and we're going to do it both by accessing some local data and accessing data from remote servers. So what I'm going to first do is set up my environment. Okay. All right, and what I'm going to do now is I'm going to CD into my directory where my data files and sample scripts actually live. Okay, so inside this directory, all I've got is, well, only 7 files. And the first thing that I'm going to do is, let's just take us through some very trivial typing of some Python. So let's say we actually want to interactively work in Python. The first thing that we're going to do is I'm just going to type Python. And if you've set up your Miniconda properly, you should see something like this, that we're running Python version 2.7.10, and now we're at a Python prompt. All I'm going to do here is, instead of doing the standard hello world in honor of Sam Eng from Metropolitan State, we're actually going to do the following. And all I'm doing is a simple printing back, and this is the mantra don't forget to GPEND. Hopefully many of you know what that means. If not, well, Google it. GPEND, it all depends on GPEND. Okay. All right, what's so big about Python? Well, this isn't too exciting, is it? All right, very trivial example. Now, let's say we want to get out of Python, run interactively here. I'm just going to type exit. Now, in the traditional Python interface, I can't just do that. It actually says use exit with parentheses or Control-D to exit. I'm just going to type Control-D. I'm back at my prompt. With most of the modern flavors of Python that are available out there, Miniconda is the one that we're using, which is just a subset of the much larger Anaconda Python distribution, comes another interactive way of entering Python commands, and it's just called IPython. So it's Python with a leading I for interactive. This gives us a little bit more information, and I'm just going to do the exact same line just to show you that it all works. Okay. Now when I type exit, it understands. I just want to get out of there. Okay, now we're going to use another really cool tool that comes available to us through the Miniconda distribution and many others. And this allows us to interactively run Python in a web browser. And this is called the IPython Notebook. And we're going to do that just by typing IPython Notebook. Now, if folks run into an issue, just put up your red sticky note. I've seen some problems with folks on Windows using Internet Explorer where things don't quite work properly. You may want to make it so Firefox or Chrome is your default browser. But if all goes as planned, if you just type IPython Notebook, it may not load quite as snappily as happened here, but what should happen is a web page will open up. And this used to be called the IPython Notebook. It is very recently changed into Jupyter or Jupyter. Anyone know really what is referred to by this acronym? Yep, David?
Julia, Python,
And R, yes. And Julia is sort of a super Python. It's kind of a new language that I think, my very limited understanding is Python, but it's really good in terms of performance. But I don't think there's a lot of libraries brought to the fore. But essentially, it's Julia, Python, and R. So having this environment set up, you should have 4 IPython notebooks visible to you. So again, at this point, if you're not seeing that, put up the red sticky note. I already see some red sticky notes on there, so maybe some folks could walk around and see what's going on there. And I'm just going to slide my notebook here a little bit. The very first thing that I'm going to try is just, once you have your IPython notebook up, just click on New. And when you see the submenu that shows up, just click on Python 2. And really, coding is just a small subset of what Jupyter Notebook brings to the fore.
You don't have stuff down
And we'll just pause a minute, get the rest of the folks on board.
I did everything in GitHub.
Well, then where did you?
I don't know, I did it Friday. I just ran everything.
Right. Well, wherever you
Hold on.
find where
But I think what we may do here is that given the fairly short time scale that we've got, and also the fact that I'll be available throughout the rest of the week to help people. If you're having some trouble initially getting your IPython notebook up and running, just hold off now and kind of watch me do what I'm doing, and I'll be happy to work with you to get things set up subsequently. So what I've done is in my Jupyter notebook, I've just clicked on New, and I've done New Python 2. And what we have here is a highlighted cell. And in this cell, what we can do is, we can do a lot of things, but one of the things that we're going to do right now is just simply run the exact same Python code that we ran interactively previously. And I'm just going to do print. Don't forget to gpend. Okay. All we need to do to execute this line of code is press the play button. That's it. Well, that's all fine and dandy, but hopefully we can do a lot more than spit back sentences. So let's take a look now at running a complete set of a complete Python program that will query a remote data server and draw a little time series. So if you go back to your Home tab in Jupyter, just click on Ezreal SST Time Series IPython Notebook. Let that open it up. Now, one of the nice things about the notebook is that it's very easy to insert non-code. And in this case, what I've done is add essentially a lot of comment lines, if you will, or just documentation telling what each line of the code does. And to the underlying notebook, or the kernel that is running Python behind the scenes, anything can be executed. And so all I'm going to do is go kind of line by line, and you will see that this is what we're doing is we're accessing a data set that's sitting at Ezreal, and it has about 35 years of sea surface temperature at, I believe, a 1/4 degree resolution every day. So we're talking about a data set that is not something that I'm going to fit on my MacBook Pro. Okay? At least not yet. Now, even comment lines, or and this is called Markdown in the Jupyter Notebook world, I can execute it. It's really not doing anything. It's just moving down through cell by cell. The first line that we're going to do is, this is actually what's called an interactive Python magic command. And what this is doing is just setting up a bunch of libraries that will enable some plotting. And it will also allow us to see our graphic generated right in this web page or this notebook, which is really cool. So that inline is what's going to accomplish that. So this first line executes pretty snappily. Now we're just going to import 3 external libraries, a plotting library, and then our netcdf package that's going to query the netcdf file. And the way I have set this notebook up is once you actually run the notebook, it's going to have all of your output, and it's going to have your graphics finished and saved for you. I wanted to kind of save the final graphic for later, so I actually avail myself of this clear output command. But now comes the point where we're going to actually connect to this URL. I mean, if you look down here, all this looks like is an HTTP URL. But when you see things like DODS in here, that's your sign that you're dealing with an OPeNDAP served data set. So I execute this file, and notice that each time we execute a line of code, we see a little asterisk appear. That's the kernel actually working. So did you see that? You probably missed it. It connected to this data set, which is gigabytes, terabytes in size, and yet in the blink of an eye, all we have now is a link to this data set. That I'd have to defer to the DAP guys for the actual meat and potatoes of how it's done. But, okay. And now we're availing ourselves of the netcdf library, and all this has done is create a pointer to this data set. And what we've done in this line is we're querying the number of variables that are actually present. Now, as I go through this particular notebook, you're going to see that there are many lines that have print commented out. What I would have folks do in their own time is run this again interactively and uncomment the print, because this is where we're going to actually see the insides of a netcdf file, what the variables actually look like, what their format is, what their size is, et cetera, et cetera. So since these are mostly commented out, you're going to see that this doesn't really take too much time, nor does it create a lot of time. So all I'm doing here is reading in the sea surface temperature data. And this is a very large array, but all we're doing is setting it up. Nothing has actually been read in. And we're going to read in our latitude, longitude, and time. And here I've cheated a little bit. I've picked a particular data point that I particularly want to look at in terms of taking a look at how sea surface temperature has changed over the years. I've got some more commented lines. Now here is, what we're doing in this very next line is, I just want to print out the value of the sea surface temperature at one particular grid point at the very last time in the file. And as we can see, there are billions of values in this data set. But I'm going to execute that, and we already have our data. Okay? And I even tried this on Southwest flying across the country on their pretty pathetic internet, and it only took a couple seconds, really, to do this. What we're doing now is there's actually about 12,000 days in this data set. What I want to do is generate a time series of just the last 10 years, and to make it so it will load fairly quickly, I'm going to only load every 15 days. That will certainly give us enough of a flavor of the multi-year variation in sea surface temperature. Now this will take just a wee bit of time now. And it'll be interesting actually to see what happens if we're all playing along here. All of a sudden Ezreal is noticing probably a big spike of data. So normally when I've run this by itself, it takes less than a minute. So this is where things can crash and burn right here. Has anyone got, as you see, you're getting a star, and once it's read in, that star should change into a number. So how many folks have gotten a number yet? All right. So they're kind of tired of me. I mean, they've obviously put me low on the pecking order, but it's good that folks are getting it. So as folks do get it.
You did?
Yeah.
Ooh,
DAP server error.
killed it.
Oh, so you got a DAP server error. All right. This is why this is not a solution that is completely ready for prime time, because what we've just done is essentially tested Ezral's data server to see if it can handle multiple user requests. And at this point, I'd have to say that job has not been accomplished. So you have probably seen this error that I got.
Yep.
Now, did anyone not get this error and just got it to go through happily? Okay. You were okay? Excellent. Well, you know, he's Kevin G, I'm Kevin T. So all we can do is try it again. And chances are, as the backlog exits, this will probably clear out. But for those of you who were lucky enough, really the rest of the plot will not take long. And I think this is cached from before. But once you actually are able to run block 11, you'll actually get a pretty nice time series. And so what we've done is we've queried a pretty ginormous data set. And when you're able to access it, it actually loads and plots the data really, really quickly. What have we not had to do is actually query, download the entire data set. I mean, we'd be waiting much longer than the time it's going to take all of us to eventually kind of dial into the NetCDF server at Ezra. So I think I'm still getting the error. Hopefully I didn't break the server down. But what I'd say is work through this example. There's really not enough time to get through most of the other examples in here in the time that's remaining. Each one of the following notebooks kind of takes you through. One reads a local file that you've downloaded in that zip file. That includes a reflectivity file that David John Gagne provided, and you'll see used more in his talk tomorrow. I also have a notebook that queries a Nomad server at NCEP that will draw for you the first 3 hours of forecast reflectivity centered over New York State, showing my Albany roots. And there is a fourth example that essentially uses the exact same code that is used in the Nomad's NCEP GRADS data server hosted data set, but is instead read from a thread server serving the exact same data. But here, in this case, you run into the issue where the translation from GRIB2 to NetCDF is different. And if you try to run the script that will work for the GRADS data server version, you'll find that it will not work for the threads version. And that's because the way that the NetCDF files are created are different. Variables are named differently. Their arrays may be set up differently. And as a result, we have to recode the script. So if we just get back to concluding the PowerPoint, what's clear is that really OPeNDAP is a technology and a service that's been available for a long time. There are programs that have used it and continue to use it. And what does Python bring to the table? Well, it brings a lot of additional libraries, many libraries that are built perhaps to leverage some of the advances in big data. I think coming up, Stefan Hoyer is going to talk about the X-ray package, which will allow even more utilization. It builds on the NetCDF4 library. But as we see, we're kind of early on the curve. It's not like tomorrow everyone's going to throw away their old tools, their visualization tools, and jump to Python. I mean, we just saw an example right here where we had 15 or 20 folks trying to hit the same OPeNDAP server, and it did not work. Clearly, we're early in the game in moving towards a Python world where we're doing a lot of essentially replacing all of our existing tools with Python. And I don't think that's where we want to go anyway. We don't want to have only one arrow in our quiver. Coming up also, Ryan May will be giving a talk on MetPy, where some of the initial steps in bringing in some of the GEMPAC grid diagnostic capabilities will be coming in. And I have some other things to think about in my look ahead over here. So once again, I'll be available throughout the week. We can go through step by step on the IPython notebooks that I didn't have a chance to show just now. And I know we want to get to lunch, but any questions that folks have right now, I'll be happy to take. Thanks.